Hello everyone, I'm Yuki Terazawa from Tokyo Institute of Technology. I talk about optimal design of a long-span spatial structure with buckling restrained braces using generalized response spectrum analysis. Recently, employing dampers are becoming common for buildings in seismic region. The challenge is which damper layer or size distribution is most effective for both seismic performance and construction cost. While equivalent linearized analysis using single degree of freedom models is popular for damper design of simple buildings, I propose a generalized response spectrum analysis-based damper optimization method for special structures with huge degree of freedoms and complex vibration characteristics. The proposed method is computationally efficient compared with brute forcing methods using nonlinear response history analysis. In this study, I talk about an application study of the proposed method to a large span music arena. As shown in this 3D view, this arena is close to a Bay Area of Yokohama City in Japan and is now under construction. The white parts compose of the substructure, and they support a 150-meter span double-layer roof. In this study, buckling restrained braces (BRBs) are placed in the substructure as hysteretic dampers. As shown in the right figure, the first and the second natural period of the bare frame model correspond to the peak of the response spectra of the design waves, considering the soil structure of the construction site. And the story drift responses of the stand frame against the random wave is the largest, because this frame is relatively heavy. The BRBs were optimized against the random waves. Two design options were initially considered. One is CBF, where the conventional braces are fully placed at all possible locations, and the other BRBF model. CBF is the most economical design option, but almost braces is buckling in large earthquake responses and damage the interiors. On the other hand, BRBF is preferable for seismic performance and continuous use, but the construction cost can easily increase. Therefore, the design company asked us for finding the best mix of conventional braces and BRBs by the GRSA-based optimization routine. Please note the numerical model has huge degree of freedom and the existing optimization method using NLRHA is much time consuming and not realistic. The design requirement was to minimize story drifts while preventing member buckling of conventional braces and to minimize the cost introducing BRBs. For reducing design spaces, the brace layer was firstly optimized from the CBF model, and the size of BRBs was subsequently optimized. In the layered optimization, elevation type and story type optimization were considered. The simple genetic algorithm was adopted as an optimization engine, and the reduction ratio of the story drift and the number of BRBs was weighted summed as a minimized fitness function. The buckling of conventional braces was considered as a penalty function. Please note that removal of CBs was allowed in the layered optimization. In the size optimization, the BRB size of the layered optimization result was optimized. In this stage, the still amount of BRBs was considered in the fitness function, and the PSO method was adopted as an optimization engine. While the initial BRBF model was selected for the elevation type layout optimization, the hybrid configuration of the concentrated BRB along both the stories and the elevations was found as the optimal solution to minimize both the story drift and the number of BRBs preventing the member buckling. Even in the layered optimization, the story drifts of the stand frame were reduced to about 1%, and the number of ERVs is reduced to 50%. It's interesting that a hybrid configuration was directly produced from the initial BRBF model in the size optimization, while the two-stage optimization technique is employed because of the computation cost. These two different optimizations produce a similar brace configuration, and this result suggested this hybrid configuration is a truly optimal solution of this arena. On the other hand, the larger BRBs were redistributed to the story with larger drift demands. Finally, the story drifts are reduced to 1.1% and the number of BRB is reduced to 37% from the initial BRBF model. The obtained results are summarized. In this study, the proposed GRSA-based tamper optimization routine was applied to the actual design project of a large span music arena, and the optimal and allowable solution to reduce the story drift demands to about 1% and to reduce the number of BRBs about 50% of the initial numbers. While the story-based concentrated BRB configuration working as energy dissipation stories is sometimes not recommended. This is because it's equal to a soft story mechanism. But the hybrid configuration of the concentrated BRB along both the stories and the elevations was truly the optimal solution for the enhanced seismic performance of this specific large span music arena. In this study, it took 1 day for the layout optimization or the size optimization by 56 parallel processes in the campus supercomputer, respectively. On the other hand, in the size optimization, the story drifts and the still amount of BRBs slightly changed on the layout optimization result. According to this result, either layout or size optimization is enough for the practical use, and 1 day is enough in real terms for the proposed tamper optimization even for large structures. The construction is now still going, and the tamper optimization result was partially employed in the final design. I would like to acknowledge to the other Sekkei engineers to give me the chance to apply my proposed optimization method to the real project, and thank you for watching this video.